In this video, I will show you a different way of approaching Lewis structures. I call it a shortcut, but as everything else in this course, I'm just going to show you a different way of approaching a problem, and it'll be up to you to decide how you want to actually solve the problem. Let's talk about how we write Lewis structures using my shortcut. Alright, so in this slide, I actually have a picture of Lewis himself, when he was a professor at Berkeley. And here on the left side, you actually see the building at UC Berkeley that is named after him, Lewis Hall. And yes, right here you have an unflattering picture of myself. You kind of depicting my own way of approaching Lewis structures. So the way I do it is a little bit more methodical, and it follows a number of steps. The first step, I identified the central element based from the components of the molecular formula. And the way you do that is by identifying the element that's present in the lowest amount. Now, if it so happens that you have multiple elements present in the same lower amount, then you go with the one that has the lower electronegativity as being the central element. Once you have identified that particular element as being central, every other element or most of the other elements will be external atoms to the central one. And what I do is I go ahead and try to determine the bonds directly bonded from the external element to the central element by using the formula here. Simply you subtract the group number of the external element from 8. Whatever that number is the number of bonds that I draw from the external element to the central one. Once I do that for all the external elements, then I switch my focus back to the central element, and I determine how many electrons, how many valence electrons the central element has or hasn't yet used up in order to make the different bonds. And simply put, what that means is that if you subtract the number of bonds from the group number of the central element, that will tell you how many electrons there are still unaccounted for, which still need to be drawn on the central element. And at the end, I complete the octet for the external elements other than hydrogen. Hydrogen will never have an octet, but every other element definitely will. So to give you an example, and we're going to start kind of simple. If we look at dinitrogen, now this only has two atoms, so it doesn't really matter which one you consider the central element. It could be the left one or the right one. It doesn't really matter in this case. But in this particular example, I'm going with the right one as being the central, completely arbitrary. Now, for the external atom, which is now the left nitrogen, what I do is I subtract the group number of nitrogen from 8. And the group number of nitrogen is 5. So 8 minus 5 tells us that we need to have 3 bonds present from the external element and going towards the central one. So we basically draw a triple bond from the external to the central element. And now we switch our attention to the central element, which we've denominated as being the right nitrogen. We simply subtract the number of bonds that we currently have from the group number of that central element. The central element, again, being nitrogen, has a group number of 5. And since we drew a triple bond, we'll have 5 minus 3 as part of our equation, group number minus bonds. And that tells us that we're missing 2 electrons on the central element. So simply what we do is we add 2 electrons as a lone pair. Okay, so you add them as a lone pair, as you can see here. And at the end, all you do is for every external atom present, you just make sure that you end up with 8 electrons on it. Right now, the fact that we have 3 bonds on the external element means that we have 6 electrons altogether. Because one thing to keep in mind is that every single line here represents a shared number of electrons, but that shared number of electrons also gets assigned to every atom that has that bond, right? So you have 6 electrons on the nitrogen on the left. You need to basically come up with 2 more electrons, and you can use the equation here, 8 minus twice the number of bonds, to come up with the number. But simply stated, you just need to come up with 8 electrons, and every bond that the element has counts as 2 electrons already. So this nitrogen had 6 electrons, you need 2 more in order to come up with 8, so you add the lone pair. And this is how you would arrive at the Lewis structure of N2 based on my shortcut. Now, there's a few things that we also need to kind of state right now, which will be of importance as we move forward with more complicated Lewis structures. And the first thing is called the octet rule. Now, the octet rule is simply an addendum to the fact that for elements that reside in the second row of the periodic table, what you're really dealing with is principal quantum number 2. And for principal quantum number 2, the angular quantum number can only have values of 0 and 1. Remember your quantum rules. L can be no greater than n minus 1. So we only have L equals 0 and L equals 1. For L equals 0, m sub L is 0. And technically we're talking about the s orbital. But where L equals 1, m sub L could be negative 1, 0, or plus 1. In other words, you go from negative L to plus L for the values of m sub L. And that tells you that you have three different kinds of p orbitals. And altogether, you have 4 orbitals present in the second energy level. Since each one of these orbitals can take up 2 electrons, at max, you can have 8 electrons. That's what the octet rule is all about. And if we look at dinitrogen, we already determined the Lewis structure. You probably do know that there is valence electrons that you can count for the elements. Since nitrogen is in group 5, you have 5 valence electrons. Multiply that times 2, since you have 2 nitrogens, you have 10 total valence electrons present. But per each individual nitrogen, you will notice that you have 1, 2, 3 bonds. That's 6 electrons, plus 2 more, which is the lone pair. That's 8 electrons. And so our dinitrogen molecule with a triple bond has 8 electrons on each nitrogen. Some of them are shared, granted, but nonetheless, each nitrogen has 8 electrons overall. If we were to draw these other forms, these other Lewis structures of dinitrogen, what we will find out is that some of them have less than 8 electrons in either one or both of the nitrogens, and that's actually a bad situation. So what you kind of want to have for these second row elements is a count of 8 electrons. That's actually pretty important. Now, another tool that we're going to be using, and in the video where I show you how to approach Lewis structures the typical way that you've learned in the past, formal charges and the octet rule are actually kind of like the tools that you have to rely on constantly. Now, formal charges, they have a fancy equation. I personally kind of like to tweak it a little bit. The formal charge is, by the way, an exaggeration of the charge of the element, and the formula is simply this: the number of valence electrons, or in other words, the group number of the element, minus the number of bonds that that element has, minus the number of non-bonding electrons. And what that means is that every dot that you see here counts as a non-bonding electron. So a lone pair of electrons counts as 2 non-bonding electrons. And this basically tells you whether you have an excess of electrons or a lack of electrons in your atom. The more negative your atom becomes, the more excess electrons you have compared to the group number of the element. And the more positive it gets, the lesser and lesser number of electrons you have compared to the group number of the element. Now, the formal charge is important, but for the second row elements, what's even more important is the octet rule. You have to fulfill that count of 8 electrons for the second row elements. Boron is the one exception that we'll talk about probably in due time. But for now, this kind of like summarizes all the big things involved in these equations. In the homeworks, you will definitely be using these equations, so keep it in mind. I'm going to some degree bypass it by showing you the shortcut, but you will probably benefit from using the valence electrons minus bonds minus non-bonding electrons formula to find out the formal charge. All right. And yes, for the 3 different forms of dinitrogen, you'll find out that for triple bonded dinitrogen, the formal charges are 0. For doubly bonded dinitrogen, the formal charges are +1 and -1. And for singly bonded, the charges are 0 and 0. So even though the first structure and the last structure may seem equivalent, the fact that the last structure fulfills the octet rule makes this a better structure than the first one. All right. Now, with that being said, I'll stop the video right here and we'll continue with other examples using my shortcut.